Hello, everyone. Welcome to the third and final part of the Chapter 4 Covalent Compounds lecture presentation. The handout, if you are using it to follow along with the presentation, we are now on page 4 of the lecture handout, where it starts a little ways down talking about electronegativity and bond polarity. So if you want to go ahead and turn to that page and have that page ready as we go through, you'll be able to follow along with the PowerPoint presentation and me. Here we go. These are some new terms for you to learn. Electronegativity. Electronegativity is a measure of an atom's attraction for the electrons shared in a bond. Now, I think we may have been misleading you a bit up until now. We've talked about how ionic bonds are formed from the complete transfer of electrons. One element completely loses the electrons and another element gains those electrons. Then we were saying with the covalent bond, the electrons are shared. And while this is all true, you might have been under the impression that the atoms were sharing the electrons equally in a bond, in the covalent bond. In reality, that's not always the case. Sometimes there's still someone who's more greedy than the other guy when it comes to sharing their electrons. And we can use this concept of electronegativity to be able to identify if one atom is essentially hogging the electrons more than the other atom that it's sharing electrons with. When fluorine, which has the chemical symbol of F, shares electrons with another atom, the electrons will hang out around fluorine's nucleus more than around the other atom's nucleus. This happens because fluorine is more electronegative than every other element. Well, what does this mean? Keep in mind that we have all of our protons in the nucleus, and the electrons are moving around outside of them. What keeps the electrons hanging out in the atom is the fact that they have a negative charge and the protons have a positive charge. And so they're attracted to each other. Well, what if I tell you that there is a stronger attraction for fluorine to pull electrons towards his nucleus than other elements have? I like to think of fluorine's house, where his nucleus is, has, it's got PlayStation and Xbox and the Switch, Nintendo Switch. It's got the fresh Cheetos, Doritos, and Fritos. All of that is hanging, is at fluorine's house. And so any electrons shared in a bond will prefer to hang out with fluorine more than the other atom. We can use the periodic table to guide us with this. We have these values that were just arbitrarily assigned, meaning somebody came up with these numbers. It's not something that can be measured like a mass or a volume where you get an exact grams or milliliters, but they are able to rank the different elements based on their attraction for the electrons shared in a bond. And what they find is the metals, those guys who love to lose electrons, well, they have the lowest electronegativity. But the nonmetals have a higher electronegativity. Remember, they're trying to gain electrons to be like their nearest noble gas. The metals want to lose electrons. So if they were convinced to make a bond, they certainly would not be trying to draw the electrons more towards them than the nonmetals are. When it comes to size, for example, if I start at the bottom of the periodic table, my atoms are a lot larger in size. They have a lot more electrons, and the electrons have had to fill out in different, farther and farther away from the nucleus where the protons are. And that's why we always say that the electrons that are the farthest away are the ones involved in bonding. When I have a larger atom, then their outermost electrons are farther away from the protons. And that makes them lose some of that attraction for electrons. When they're trying to recruit them over, Somebody coming over might be like, well, man, I can barely see the protons in the nucleus. I'm not sure I really want to hang out at your house a whole lot. But if they go to Fluorine's house, look at him at the top of that row of the group, 7A. He's little, much smaller. And so any electrons that'll come hang out with him are pretty close. I think they're in what, the second row of seats? I mean, it's a great view. And therefore, electrons shared in a bond will definitely be more interested in hanging out in his house than someone else who's larger or more towards where the metals are on the periodic table. Oxygen, he's about the same size as fluorine, and so his electronegativity is the second highest. Then we have chlorine, who is the third highest. He's one electron away from being stable, so he'll definitely be trying to attract electrons over to his house too. But fluorine, he takes the cake. Anybody with fluorine is going to just have to be mentally prepared that their electron and the electron they're supposed to be getting from fluorine really won't be coming to visit anywhere near as much as they go to visit fluorine's nucleus. This is going to be important, so bear with me. If the electronegativity and the sizes of the two bonded atoms are equal or at least similar, we call the bond that they form a nonpolar covalent bond. You can think of the polar, when you think of like the North Pole and the South Pole. I don't know if you know that they're actually magnetic poles, just like a positive side of a battery and a negative side, or like a magnet, if you know that a magnet has a positive side and a negative side. And so I think of poles, or you could even think of maybe bipolar, having two ends to it, a positive end and a negative end. With nonpolar, that's the same as saying that there's no difference between the two sides. And that's what I would expect to have if there's an equal attraction for the electrons in the bond by both atoms that are bonded together. Again, if they both have a similar or exactly the same attraction for the electrons in the bond, and that's going to be based on their electronegativities and technically on their sizes too, although the textbook doesn't get into that as much. The electrons that they're sharing will be shared much more equally with each other. And so we won't have a more positive side or negative side. The electrons with their negative charge are flowing back and forth equally, no difference, nonpolar. This nonpolar bond here between two carbon atoms is going to be exactly the same electronegativity, exactly the same size atoms. So that's about as nonpolar as you can get. On the other side, this one is the one that I really need you to know is nonpolar. The bond between carbon and hydrogen is nonpolar, even though the carbon atom's larger and the hydrogen has a slightly less or slightly lower electronegativity. The experiments have shown that we can consider those two atoms to equally share the electrons in the bond. That's really important for you to know. The electrons in a nonpolar covalent bond are being shared equally between the two atoms that are bonded together. I need you to know that bonds between identical atoms are nonpolar. I also need you to know that the bonds between carbon and hydrogen are nonpolar. Now, here's where we get into a little bit of trouble. Technically, any bonds between any other combinations of nonmetal or metalloid elements should be considered polar. Why am I saying that this is an issue? I'm saying it's a problem because your textbook says that the bonds between carbon and sulfur and hydrogen are nonpolar. And I'm going to write this down because it's going to be confusing possibly for you doing the assignments. So I need you to have this information straight. So hang on just a second. I'll be right back. I'm back. So about these nonpolar covalent bonds, the two electrons in the bond are being shared equally by the two atoms that have the bond. Everyone agrees that covalent bonds between identical atoms are nonpolar. Examples would be a bond between two carbon atoms, two fluorine atoms, two oxygen atoms. It's a nonpolar covalent bond. And I can say nonpolar bond, same thing. We don't have to keep saying covalent. There is no such thing as a nonpolar ionic or polar ionic. Those don't go together. Covalent bonds between carbon and hydrogen, C and H, are nonpolar. Everyone agrees on this. What people don't agree on, or what not everyone agrees on, is whether the bonds between carbon, sulfur, and hydrogen are always nonpolar. So I'm going to write something else down. Be right back. So what I want you to know is that the textbook and a video that I like that I'm going to show you, they both say that the bonds between carbon and sulfur and hydrogen are nonpolar covalent. Almost everyone else says that these are polar bonds. It has to do with the size of the sulfur atom and the fact that it's much larger atom than the carbon and hydrogen atoms. If you're trying to do the Chapter 4 Learn Smart assignment on Connect, which is based on the textbook, remember that's optional, but I did add it this semester in case it might be helpful to you. I liked the questions that I saw from it. You may be asked if the carbon sulfur and sulfur hydrogen bonds are polar or nonpolar. You need to say they're nonpolar. You also need to do that if you're doing any additional practice problems from the book. I will not give you problems with CS or SH and ask you if the bonds are polar or not. They are, but I'm not going to try to trip you up and trick you if you've been studying the textbook and then I'm telling you that the textbook's wrong. I'm not going to purposely try to trick you on that. So I wanted you to see this and know the truth, well, or what's more widely accepted. That's the thing about science and why it gets confusing for a lot of the general public to understand that we're constantly doing new experimentation and discovering new things. And while we may have seen something always occur the same and experimentations that we've done so far are always showing the same thing, and we can be pretty confident about what we're saying, you'll find that the majority of good scientists will say that they can't be 100% sure, that nothing in science is 100% sure. And that's because we realize that there's always more for us to learn. Same with this. I want you to know that the majority of information you'll find will say that these bonds are actually polar, but your textbook and that one video I'm doing say they're nonpolar, that the electrons are being shared equally, but I will avoid tricking you. If you catch me tricking you, it was unintentional, and let me know. Okay, back to the rest of the presentation now. So I was just thinking this is probably why I haven't done the Learn Smart assignments before, but I know a lot of you are going to be using your textbook as a reference, and this may lead to confusion. So my goal, and what you'll see me constantly saying from here on out, is that I want to try to narrow it down to you that there's only two options for nonpolar bonds. That's going to be between identical atoms and between carbon and hydrogen. And I want to just leave it at that. And we're not going to talk about the carbon sulfur and sulfur hydrogen bonds as being nonpolar anymore. Okay, so what happens next? Well, there we go. If I have two atoms that are bonded together, covalently bonded, but they have different electronegativities and or the size of the atoms, the difference in size plays a role, we are going to end up with a polar covalent bond. It's also known as a dipole. So dipole, di meaning two, as we know from naming our covalent compounds, meaning that there is a positive side and a negative side. And An example would be a bond between carbon and oxygen. That's not between two carbon atoms or two oxygen atoms. It's not between carbon and hydrogen. So immediately I know that it's a polar bond. The electrons in that bond, the one valence electron being shared by carbon, the one that oxygen is sharing, they are not being equally shared. It's like, yeah, sure, buddy, you can borrow it, but only like a fourth of the time. I get it the rest of the time, and I get yours the rest of the time. Unequal sharing there. The electrons in the bond are being pulled towards oxygen, the more electronegative atom. Remember, he's right next door to fluorine, second most electronegative element that there is. We can show this two different ways. One is by doing this symbol. It's the Greek symbol for the lowercase d, for delta. And so we call it, hold on. We call it delta positive or delta negative. This one's delta negative. We say that oxygen has a partial negative charge. I don't just put a negative sign next to the oxygen. He doesn't have permanent custody, 100% custody of the electrons in the bond, like you would with a metal. He has temporary custody, but he gets to see the electrons a lot more than the carbon does. This gives him a partial negative charge from having the negative electrons hanging out around his atom, around his nucleus, more than at carbon's. Well, carbon came along and is sharing one of his electrons with oxygen, and now his electron's hanging out more at oxygen's house. Well, when that happens, carbon ends up with a partially positive charge. And this happens because carbon is less electronegative than oxygen. He's several spots away on the periodic table from fluorine. I like these color representations. When I take two hydrogen atoms or two of any element and have them, of any non-metal element, and have it bonded to itself. For example, all of those diatomic elements, the Brinkelhoff or Super 7, they all are going to look like this. They will share electrons with themselves equally because they have identical electronegativities and size. And the electrons then will be spread out around those two atoms equally. And we say that in terms of having a dipole, where there's a positive side and a negative side, these guys have zero. That's the dipole moment equals zero. Now, I can have a polar molecule where I have a bond between hydrogen and fluorine, where fluorine is much more electronegative than the hydrogen. The electrons are being attracted or pulled more towards the fluorine atom. Notice how this arrow is being drawn. The arrow is pointing to where the electrons are being drawn. And it leaves this little cross that looks like a positive sign on the side of the molecule or the side of the bond, where we have our partial positive charge. The partial negative charge is over where the arrow has pointed to, where the electrons are being attracted to. Usually we don't use both symbols, it's one or the other. Either we use the arrow or we use the delta plus and delta negative signs. But here they're reinforcing it three different ways, with colors, with an arrow, and with the Greek symbols for delta. I saw this one, I thought it was cute. The hydrogen atoms are sharing their electrons equally. And now here I have hydrogen with chlorine. Chlorine is the third most electronegative element. And so he's dragging his own electron back, plus the one that electron's sharing, and hanging on to them more than the hydrogen is able to do. What partial charge then will that put on the chlorine atom? Will he be partially positive or partially negative? And what type of charge will we see on the hydrogen? Partially positive or partially negative? You're right, says Dora the Explorer. The chlorine atom will have a partially negative charge. It's dragging his own electron and another electron towards him. He doesn't get a full negative charge, but he does have a partial negative charge. The hydrogen, meanwhile, well, heck, he's almost losing custody of the one electron he showed up with. So he's losing that negativity a lot of the time, which will give him a partial positive charge. The page 126, table 4.3, they use actual numbers. What I want you to realize, because I don't want you to have to memorize or even look at the electronegativity diagram again, I think just being able to look at a periodic table is enough. What I need you to know is if we have a small difference, or the smallest difference between the electronegativities, again, that's going to be between identical atoms or between carbon and hydrogen. The electrons are equally shared and they are nonpolar bonds. Any other bond between two different elements, other than carbon and hydrogen, you can assume it's a polar bond. The electrons will not be shared equally. And then if there's the largest difference between them, where we're with a metal who says, here, take the electron completely, and my non-metal standing there going, okay, sure, I want it anyway. Then we're going to form ions and have an ionic bond. We've looked at bonds, the covalent bonds being polar or non-polar. We're going to expand it now because while some of my covalent compounds or molecules are going to have just one bond in them, say one polar bond or one non-polar bond, a lot of our covalent compounds and molecules, they're going to have more than one bond. And things happen if you have more than one polar bond. So let's take a look at how molecules can be non-polar or polar covalent too. This is extremely important that you understand this, because a lot of what we're going to be doing in later chapters, say chapter 7, chapter 8, when we get to the organic and biochemistry chapters, they depend on you being able to know if a molecule is nonpolar or polar, or if a compound's ionic. But we already talked about how to do that. Let's watch this video. I'm pretty sure this is the one that I like to watch. So I'll be right back with you. Let's take a look at this video now. It's not the one I was thinking of, but let's take a look at this one.
When atoms form a covalent bond, they do not always share their electrons equally. This is because atoms differ in their electronegativity, or their ability to attract electrons. Consider what happens between atoms of chlorine and sodium. Chlorine has a higher electronegativity than sodium. As a result, it strips an electron from the outer shell of the sodium atom. The sodium readily surrenders the electron to chlorine because it has lower electronegativity. A more important example of the importance of electronegativity occurs within a molecule of water. Water is composed of 2 atoms of hydrogen and 1 of oxygen. Of these 2 elements, oxygen has the greater electronegativity. Because of this, the electrons that are shared in the covalent bond between the oxygen and hydrogen atoms are attracted more towards the oxygen atom and thus spend, on average, more time orbiting the oxygen atom than the hydrogen atom. Since electrons have a negative charge and spend most of their time near the oxygen atom, the oxygen atom itself takes on a slightly negative charge, and the hydrogen atom becomes slightly positive. This causes the bond between the oxygen and hydrogen to become polar. The term polar simply means that the atoms on either side of the bond have a partial and opposite charge. Now let's put this water molecule in an environment with other water molecules. Notice that the water molecules orient themselves so that the negative end of one water molecule is opposite the positive end of another water molecule. When water molecules orient themselves in this manner, a weak attractive force called a hydrogen bond is formed. In water, hydrogen bonds are abundant. Each water molecule can engage in as many as 4 hydrogen bonds. However, hydrogen bonds are weaker than covalent bonds and therefore tend to be temporary, breaking and reforming constantly. In water, the large number of hydrogen bonds and their temporary nature is what gives water its unique characteristics and makes it the basis for life on Earth.
So I just want to play one more line one more time because I think she did a great job saying again what this bond is.
Is the bond between the oxygen and hydrogen to become polar. The term polar simply means that the atoms on either side of the bond have a partial and opposite charge.
Okay.
Now let's put this water molecule in an environment with other water molecules.
All right. So with the ionic bonds, they have a complete positive and negative charge. With a polar bond, they have a partial and opposite charge. They're not completely positive, they're not completely negative, but the two atoms that are sharing the electrons will create a polar bond or a dipole, D-I-P-O-L-E, because one will be more partially negative and the other will be more partially positive. While I've got this huge image on my screen, I want you to take a look at the entire molecule. Do you see how up here across the top, this is the partially negative side of the molecule where the oxygen is? And down here, where the electrons are not hanging out as much, the partially positive area of this molecule is down here. We have two sides to this molecule, a partially negative side and a partially positive side. That makes the entire molecule a polar molecule. Not only is it because it has polar bonds, but it has to do with the orientation of the molecule. It's not symmetrical. There's a partially negative side and there's a partially positive side. That makes this a polar molecule. Since I like this phrase so much, why don't we make this the thing for today, or for this presentation? We'll make it the thing I'll ask a question about. And so I'll have different ways that you can describe a polar bond, but we're going to use this particular one from this video, that polar simply means, let me rewind it one more time, for our participation grade, the term polar simply means that the atoms on either side of the bond
have a partial and opposite charge.
They have a partial and opposite charge. I don't have that written anywhere else phrased quite that way in my notes. I like it. I like that it's pointing out that it's not a full charge. And of course, we still have an opposite charge that creates the attraction that keeps those atoms covalently bonded together. Okay, so let's go back now to the presentation, and I'll be right back with you. All right, let's see what happens next. The polarity of small molecules. The reason why I'm pointing out small, which you probably won't see in the textbook or somewhere else, is because soon we are going to be talking about large molecules, that things like proteins and fats and oils, and we may have some polar regions to them and non-polar regions to them, but I won't be able to say that the entire molecule is polar necessarily. I might be able to say that the entire molecule is non-polar, but when we get really large, it's going to be times where there's going to be different sections of the molecule that are polar or nonpolar. For now, we're going to keep everything on the small scale. So something that's just got a few atoms, a small molecule, then I can decide whether the entire small molecule is polar or nonpolar, not just one part of it. Remember, we're going to be looking to see if there's a partially positive side and a partially negative side to the molecule. Just like I checked with the bond, now we're going to expand it to the molecule. And so it's going to depend for a molecule, whether it's polar or nonpolar, is going to depend, first of all, just on the polarity of the individual bonds. If I don't have a polar bond anywhere in the molecule, then it's impossible for the molecule itself to be polar. We've got to have somewhere where the electrons are not being shared equally. But that's only one piece of the puzzle. The other part of the puzzle is the overall shape of the molecule. I just showed you how water, the oxygen atom was on the side that was more negative, and the hydrogen atoms were on the side that were more positive. That shape created a positive side and a negative side to the molecule. Not every molecule is going to be able to do that. There are several examples of molecular shapes of molecules. We are not going to get into that, and we're not going to have time at all this semester to get into it, unfortunately. Molecules are not necessarily flat or linear, straight line, or anything like that. In fact, while some are flat and could be drawn flat on a page, and I could pick it up and look at it like a piece of paper, a lot of molecules aren't like that. They are spread out in different regions of space. They have a three-dimensional shape that points in different directions. That kind of arrangement can make a difference when I'm trying to decide if a molecule is polar or nonpolar. You're not going to be required to know these shapes or their names. We don't have time this semester to go over it. Again, I won't really be able to do it at all with the organic chemistry unit. Sorry. What I do need you, though, to do is look for symmetry or balance across the molecule, and I'm going to give you some help with this. This is where knowing how to draw the Lewis structures for these molecules will be very important. When we get a formula C2Cl2, this is one of the ones I showed in the previous lecture presentation. It's one, maybe not with chlorine, but it's one where we have two carbon atoms that are triple bonded to each other, and then each one is single bonded to another atom. In this case, the outer atoms are identical. They're both chlorine atoms. They have equal and opposite dipoles. So it's a straight line. The electrons in the carbon-chlorine bond are being pulled towards the chlorine atom, both on the left and an equal amount on the right. We say then that the dipoles cancel. When they are in equal but opposite directions, they will cancel each other out. And remember, a dipole is just another way of saying a polar bond. If the individual polar bonds, these dipoles, cancel out in a molecule, the molecule is nonpolar. Even though this molecule has two polar bonds, the ones between the chlorine and carbon atoms, it's still a nonpolar molecule because of its symmetry. In this molecule of methanol, it looks a little bit like the water, doesn't it? Where the oxygen atom has two single bonds coming down, but instead of them both being to hydrogens, one of them is being to a carbon, who is then attached to three hydrogen atoms. That's what this means. H3C means I have a carbon attached to three hydrogen atoms. Now that portion is nonpolar. Those guys, the carbons and hydrogens, share electrons equally. So it's almost like having a hydrogen over there. The arrows are letting us know that oxygen is more electronegative than the hydrogen or than the CH3 group. The electrons are being attracted toward the more electronegative oxygen atom, and we've created two polar bonds, but this time they're not canceling each other out. In fact, they're reinforcing each other. They're all headed in the same direction, just like in water. We'll have a partially negative side to the molecule where the oxygen is, and a partially positive side of the molecule where the hydrogen and the carbon with the three hydrogens are attached. In this case, the individual bond dipoles do not cancel, and so my molecule is polar. Polar meaning it has a partially positive side and a partially negative side. Nonpolar covalent molecules generally have. Now I just have three things for you to remember. They have only nonpolar bonds, which means they have identical atoms, or they are only made of carbon and hydrogen. Or they have a central atom with no lone pairs and identical atoms surrounding it. And I'm able to break this down even farther for you guys and just let you know if it's carbon or boron in the center. And it could be two carbon atoms in the center, like we saw just a minute ago with the two carbons that were triple bonded together. Here, I'll show you again. This guy here. I'm pointing to my screen. This guy here, I think of those two carbon atoms as being a central atom. So they're at the center of the molecule. They themselves are nonpolar with each other. And then the surrounding atoms, the two chlorines, are identical to each other. They're both chlorine. With that, we have the central atom, the carbon. He has no lone pairs of electrons. He doesn't have any valence electrons that he's not using for bonding. The other atoms around it are identical. They're both chlorine atoms. That has created a nonpolar molecule. What would happen if instead of these both being chlorine atoms, what if one was chlorine and one was hydrogen? Well, then I'd have my chlorine atom hogging these electrons in this bond, but with a hydrogen there, the carbon and hydrogen share equally. They don't create a polar bond. So now I would have a polar molecule again. Or say one was chlorine and one was fluorine. Well, fluorine pulls the electrons toward it more than chlorine does. We wouldn't have the equal dipoles canceling out. It'd be like trying to cancel out a 7 and a 6. They don't quite cancel each other out. We have something left over, so we have a polar molecule when they're not identical atoms on the outside. Classic examples. I highly, highly, highly recommend that you put these on a note card. You're taking open book tests in this class. You not have open internet, right? But you do have open book and open note tests. You really, really, really should have these written down for easy reference. Oxygen, which is two oxygen atoms bonded together. Carbon dioxide, a carbon, and on each side of them is an oxygen atom. Carbon tetrachloride, carbon with 4 chlorine atoms attached to them. C2Br4, 2 carbon atoms bonded to each other, and then they each have 2 bromine atoms. Could also be 2 chlorine atoms, or 2 fluorine, a total of 4 chlorines, 4 bromines, 4 fluorines, same effect. BF3, classic. Again, though, it doesn't have to be fluorine that's on the boron. It could be 3 bromine atoms or 3 chlorine atoms. Those guys are all in the same group. They're all halogens. And so the molecule would be very much the same, but they have to all be identical. And then methane. It's just carbon and hydrogens. Anything where you just have carbon and hydrogen, C2H6, C20H, what would be 44, anything like that, it's going to be nonpolar when there's only carbon and hydrogen atoms. If a covalent molecule does not have either of these two characteristics, either only nonpolar bonds or the central atom with no lone pairs and identical atoms surrounding it, you can assume the molecule is polar. I have really, really condensed this. It's rare to be able to find this information brought down to this level. There's going to be exceptions, but not for this course. Okay, so please try to get this somewhere where you can work with it. That if there aren't any polar bonds, the molecule is nonpolar. If there are polar bonds, but the guy in the center is carbon or boron, and it could be two carbons or two boron. Well, no, not two bonds. It could be two carbons. I mean, I guess it could be two boron atoms. I don't mean to badmouth it. And everybody around them is identical. That's going to be nonpolar as well. The rest are polar. Look at this guy. This is formaldehyde. That's stuff that we can store body parts in. I mean, you really shouldn't anymore because it's toxic, but it's only got one polar bond. It's a double bond, but the electrons are being pulled from the carbon toward the more electronegative oxygen. There's nobody else there to cancel it out. The carbon-hydrogen bonds are nonpolar. This small molecule then is a polar molecule. BF3. The boron has 3 polar bonds with fluorine atoms. The electrons are being pulled out, but the electrons are being pulled away from the boron in 3 directions to an equal amount. They cancel each other out. The entire molecule as a whole would be green. Everybody would be sharing the electron, well, or maybe like red all the way around the outside. It would be uniform, it would be symmetrical, and it would be nonpolar. This one, the central atom, is not boron or carbon. It has a lone pair of electrons on it. We lose our symmetry. We have electrons, the lone pair of electrons are pushing the hydrogens down. It's taking up a spot. It's not going to balance itself out. It's not symmetrical anymore. In fact, it's more like water, where the electrons are all being pulled towards one location. Those dipoles are reinforcing. We have a much more partially negative side and a partially positive side to this molecule. It is a polar molecule. NH3, classic polar molecule. Dichloromethane, 2 chlorine atoms, 2 hydrogen atoms. Even though it has carbon at the center with no lone pairs, the outer atoms are not identical. This is going to be a polar molecule. On the side of the molecule where the chlorine atoms are, that's going to be more partially negative. The side where the hydrogen atoms are, that's going to be more partially positive. We have a polar molecule. In general, in a small molecule, if you have an oxygen, you can assume it's going to be polar. He's got that whole bent kind of look to him, pulling the electrons up, except for O2, because then it's a bond between identical atoms, and CO2. We're going to take a look at that molecule. In fact, it probably is one of the ones you're drawing with your Lewis structure homework. That one is very symmetrical, and the dipoles cancel out. So O2 and CO2, they have an oxygen, but they're nonpolar. Pretty much everything else, if it's small, it's going to be a polar molecule, or if it's larger, it's going to have a polar region, anywhere you see an oxygen. With nitrogen, I haven't seen anywhere the small molecule is not polar, or in the larger molecule, when there's a nitrogen, it's going to have a polar area to it. The exception to that will be NH4 with a +1 charge. That's our ammonium, and that needs to set off alarm bells in your head. Ding, ding, ding. NH4 +1, that tells you you're working with an ionic compound. That's not going to be a molecule. When I see NH4, I know it's ionic, and I don't deal with any of this. Ionic compounds are not polar or nonpolar. It doesn't go together. Remember, polar means you have a partially positive side and a partially negative side. You don't have individual ions. Lastly, if you have a halogen, which we represent with the letter X, that's the fluorine, chlorine, bromine, iodine, found in group 7A on the periodic table. If you have those, it's almost always polar, unless you're dealing with the idea where you have a carbon atom or more than one carbon atom in the center, and all of the halogen atoms around the carbon or carbons are identical. Then you get your symmetry back, like we had with the triple bonded carbons and the 2 chlorine atoms. Then they're nonpolar. But most of the time, you're going to have a polar molecule when you have it. The other exception I was just noticing is if I have the boron in the center. So I need to update this. That's a little bit late now. So if I have boron in the center and everybody outside is identical, it'll be nonpolar as well. I included this with your handout. This, some of you will just have your note card that says classic polar, classic nonpolar, what to look for. Some of you may like to have a flowchart like this to follow through with each molecule. So let's say, for example, we worked with water, H2O. Well, there's no metal in there. Oxygen and hydrogen, both nonmetals. There's certainly not ammonium in it. So no, there's no metal, no ammonium. That makes it a covalent molecule. Okay, H2O, water. Are all the atoms of the same element? No, we have 2 capital letters, the H and the O. All right, well, let's move on to the right then. Does it have only carbon and hydrogen atoms? No, we're talking about H2O. It's got an oxygen in there. So we're going to keep staying to the right. Is the central atom surrounded by identical atoms? Why, yes. Yes, it is. The oxygen has 2 hydrogens on it. So let's go towards yes. Does the central atom have any lone pairs? Oh, yeah. Oxygen always has a couple of lone pair electrons on him. So yes, he has some lone pairs on him. The molecule is polar covalent. And that's exactly what we were saying before. Water has a partially negative side where the oxygen is, a partially positive side where the hydrogen is, due to unequal sharing of the electrons in the bonds. So water is a polar covalent compound. Now I could do something where, let's say I had benzene, C6H6, just carbons and hydrogens. I start at the top. There's no metal, there's no ammonium in it. So it's a covalent molecule. Are all the atoms of the same element? No, there's 6 carbons and 6 hydrogens, 2 capital letters. Oh, does it have only carbon and hydrogen? Why, yes, yes, it does. There's no oxygen, nitrogen, there's no halogen. So C6H6 is a nonpolar covalent molecule. So I hope this will help you, but we'll probably play around with this a little bit during our live sessions and have that help us out as well. I think this is the last slide. Let's see. It sure is. So this is the end of this presentation. I expect that we'll be doing some more of this during the live sessions, as I said, and you must be good at this if you want to do well in chapter 7 and chapter 8 and the chapters after that, like chapter 13, 19, and 21, the biochemistry stuff. So please make sure that you're comfortable with this information. My goal was to give you lots of problems on the lab and other places so that you can get good at identifying whether a molecule is polar or nonpolar. Let me know if you have questions. Otherwise, I hope to see you during one of the live sessions coming up. Thanks for watching.